In this video, we will consider the scattering of radiation, electromagnetic radiation, by free electrons. It was observed that when incident radiation falls upon the metal which contains free electrons, we get free electrons and incident radiation along with the scattered radiation. The scattered radiation has wavelength which is longer than the incident one. Similarly, the frequency and energy of the radiation which was scattered has got lesser value. To understand this, an effort was made that how energy and momentum of the electromagnetic radiation or electromagnetic wave is related. So here we see that you see this equation E equals to Cp. So energy of the electromagnetic radiation is related with the momentum of the wave by this relation, and you see C is the velocity of light in vacuum. Similarly, if we consider the theory of relativity, then one sees that energy of the particle is related with the momentum and mass of the particle, and the relation that one gets is E equals to C whole under the root square m0 square c square plus p square. Here m0 is the rest mass of the particle that you are considering. Now suppose we put m0 is equal to 0 for the zero mass system or zero mass particle, then we will get the relation as we saw above, E equals to Cp, and that's why we say that the electromagnetic radiation, the nature of this given by Maxwell's relations or Maxwell equations is consistent with that of theory of relativity. Now let us see that we consider a model in which electromagnetic radiation falls on the electron, and electron completely absorbs this radiation and gets scattered. Then what happens? We have to check kinematically that momentum should be conserved and energy should be conserved. Then what is the momentum of the electromagnetic radiation? It is E by C, which is very high. Now momentum earlier and momentum later on, that is benchmark is scattering, then energy momentum of the electron should be equal to momentum of the photon, incident photon, but that is very high, so momentum conservation is at the stake. Similarly, if you see the energy, then energy of the electron, kinetic energy of the electron, should be given by this relation Ek equals to C under the root mec square m square plus pe square minus mec square. Me is the mass of the electron at the rest. Similarly, what is the momentum of the electron? Then momentum of the electron Pe must be given by E by C, and that's where we see that the problem comes that these energy and momentum conservation laws are not properly taken account of. Similarly, now let us consider the nature. If I take the incident radiation, then it has got the peak at angle theta is equal to 0, that defines our incident direction. And later on, if we put our detector at theta equals to 45, then you see that we get the two peaks in the detector one at the angle theta is equal to 0 and another at theta is equal to 45, and these two peaks are correspondingly of the incident radiation and the scattered radiation. Similarly, you can consider the other cases also where theta equals to 90 degree, and the same way theta equals to 135 degree for the scattered radiation. This effect is called Compton effect. That is, here we have to adjust our hypothesis, correct our hypothesis. And what should be our hypothesis now? That energy momentum radiation that was incident, it was also present after scattering, and therefore after scattering we get two types of radiation, incident radiation and the scattered radiation at the particular angle, as well as we get scattered electron, which was earlier in the metal. Now it is free and it is flying. We can understand this effect, that is Compton effect, by considering the kinematics or energy and momentum considerations. Now let us see what is the energy, what is the momentum before scattering. It is P vector, and what is the momentum after scattering? It is P prime vector plus PE vector. P is the momentum of electromagnetic radiation, or that is quanta of electromagnetic radiation, i.e. photon, and P prime is the scattered photon. Similarly, momentum of the scattered free electron is PE. Now what is the momentum, what is the energy? Now energy can be written as energy of the radiation, E, plus rest mass energy of the electron, that is MEC square. After the scattering, energy of the radiation, that is E prime, and after scattering, energy of the free electron, that is C under the root ME square C square PE square, that means this term. So now we have written our equation for momentum as well as energy conservation. Now we want to know the value of PE vector, which is P minus P prime, that is here. Now if I square it, because these are the vector equations, so I get PE square, equals to P square plus P prime square minus 2P P prime, and if I put P equals to E by C, then I get the equation 1 over C square bracket E square plus E prime square minus 2 E prime cos theta. And then we can further solve it to get PE square equals to E plus MC square minus E prime whole bracket square upon C square minus ME square C square from the relation of the energy conservation. And then eliminating PE from these two equations, we will get the equation E minus E prime equals to E prime upon MEC square bracket 1 minus cos theta factor. Now we are going to divide the whole equation by E prime product. Then we will get a nice relation, which is 1 upon E prime minus 1 upon E equals to MEC square 1 minus cos of theta. This is called Compton relation. Now you see here, what we have assumed here is that electromagnetic radiation behaves like a particle of energy E equals to h nu and momentum P equals to E by C, and it is moving in the vacuum with velocity of light, and it is behaving like a particle. So this photon strikes with free electron, which is within metal surface. Now it is ejected from the metal surface, so we get the scattered electron and we get the scattered photon of lesser energy and frequency. Now you see here, putting these relations, the Broglie relations, we get 1 upon h nu prime minus 1 upon h nu equals to 1 upon mec square bracket 1 minus cos of theta. And if we eliminate Planck's constant, then we will get the further relation in terms of frequency, 1 upon nu prime minus 1 upon nu equals to h upon mec square bracket 1 minus cos of theta factor. If you put nu equals to nu lambda equals to c, then you can draft this whole equation in terms of the wavelength also, and we will get lambda prime minus lambda equals to 1 upon h upon mec and multiplied by the bracket factor 1 minus cos of theta. So here we see that Compton relation relates the dynamic quantity after scattering, before scattering, and this is in terms of the angle, scattering angle theta, and Compton wavelength. What is Compton wavelength? Compton wavelength is known as h upon mec. Me is the rest mass of the electron. And therefore, if we now go and see study the Compton effect profile, then we will see that if lambda is the wavelength of the incident radiation, then at theta after scattering, the scattered photon has got the wavelength lambda prime, and this relation is satisfied, and we will see the two peaks for incident, one for incident and one is for the scattered wavelength. This is what we see in Compton effect. Now in the next lecture we will consider the pair production. Thank you.